Welcome back, my dear students. In last class we derived, in last previous three classes in videos, we derived three expressions. One expression due to self weight, one expression due to circular tapered bar, one expression due for rectangular tapered bar. Okay, we have three different problems in today's lecture, and they all depends on these derivations only. Okay, now see here. The bar of uniformly tapered, yes, tapers from a diameter andre circular bar it is. That 20 mm at one end to the 10 mm at the other end over an axial length of 300 mm. Length is 300 mm. This is subjected to an axial compression of 7.5 kilonewton, where Young's modulus is given 100 kilonewton per mm square. Determine maximum and minimum axial stresses in the bar and total change in the length of the bar. Total change in the length of the bar. Okay. See here, this bar is something like circular here, and it is tapered like this. This is tapered like this. Then here some load, here it is almost 7.5 kilonewton, and here also 7.5 kilonewton. Then here the diameter is 10 mm, 10 mm. Here the diameter bigger is 20 mm. The total length here given is 300 mm. 300 mm. Right? Then what else? And Young's modulus is given. We will directly input and determine the maximum and minimum axial stress. Stress formula is force by area. Force by area. Then here the force is same. From here to here force is same. Only area is changed. Here small area is there. If area is a very small, then the stress will be more. If the area is very large, then the stress will be very less. Therefore, we will substitute P as a 7.5 kilonewton only. Area, two different areas are there, that we will substitute. Then here A1 is this side is pi by 4 into 10 square. That is 78.5 mm square. And here A2 is pi by 4 into 20 square. That answer is 5 into 20 square, 314. This is 314 mm square. Okay, now I got A1 and A2. Therefore sigma max will be equal to 7.5 into 10 raised to 3 is the load divided by area. Area is how much here? 78.5. The answer is 7.5 into 10 raised to 3 divided by 78.5. Answer is 95.54. This is 95.54 MPa or Newton per mm square. Then sigma minimum equal to 7.5 into 10 raised to 3 divided by 314 equal to 7.5 into 10 raised to 3 divided by 314, that is 23.88. 23.88 MPa. You got maximum and minimum stress. This is over, this is over. Then the total change in the length of the bar. In previous class we derived expression, that is a 4p by pi d1 d2 e. That answer will be 4 into 7.5 into 10 raised to 3 divided by pi. D1 is 10, D2 is 20, E is 100 into 10 raised to 3. The answer will be 4 into 10 raised to 4 into 7.5 into 10 raised to 3 divided by pi into 10 into 20 into 100 into 10 raised to 3. The answer is 4.77 into 10 raised to minus 4 mm. Okay, let me check once again. I am confused whether this answer is right or wrong. We'll check. Oh, one mistake we did, right? What's that mistake? Here L I need to write now. Then here L I need to write. Therefore the L is 300 mm. Therefore this is the wrong answer. Into 300. 0.143. Point I love you. Right? 0.143 mm. Okay, this much. Here I'm sorry, I forgot here L, therefore this is this much. Next problem will go. Here an aluminium flat of a thickness 8 mm and an axial length of 500 mm has a width of 15 mm tapered to 25 mm over a length. It is subjected to an axial compressive force P so that the total elongation of the bar of flat does not exceed 0.25 mm. What is the magnitude of P if E is this much for an aluminium? Here they did not give a P value. They are asking you how much P should be applied so that the total extension will be this much restricted. Means here delta L is given, P is not given. P is not given. Okay, no problem. First we'll understand the problem. The thickness is varying. The breadth is varying. Initially it is here a 15 mm breadth. Then later it become a 25 mm. Therefore it is a tapered. And the thickness is how much? Here small thickness will be there. No, here small thickness will be there. This small thickness it is given 8 mm. 8 mm means it is a T. This is the B2 and this is the B1 and this is the length L equal to 500 mm. This is the length and then P is not known. Therefore your delta L formula will be PL upon TE B2 minus B1 into ln B2 by B1. Okay, this is known to us 0.25 equal to P is not known to us. L is 500 divided by T is 8 mm. E is 67,000. TE is over. B2 minus B1 is 25 minus 15. Then ln 25 by 15. Then here I will calculate only the numericals which I know. That is ln first, ln 25 by ln bracket 25 by 15. This into 500 divided by 8 into 67,000 into 25 minus 15 is 10. 10. Then this answer will be 4.765 into 10 raised to minus 4 P. This is 0.25. If I send this entire thing this side, then I will get P equal to 0.25 divided by answer. Then I got P as 5,246 Newton. I can call this as P equal to 5.246 kilonewton. This is a P. Means this much only a load I can apply for that, so that it will be okay. If I apply more than 5.246, then it will exceed 0.25 mm. Therefore that is correct answer. Then we'll go to the third problem. Very interesting. The tapered not. It's a stepped steel bar is suspended vertically. The diameter in the upper half portion is 10 mm. Yes, it is shown here. And while the diameter in the lower half portion is 6 mm, shown here. What is the stresses due to self weight? Stresses due to self weight in the section B. In the section B here, what is the stress due to self weight here they are asking, and at a point A here how much it is they are asking. As shown in the figure, E is a 200 kilonewton per mm square, weight density is this much Newton per mm cube. What is change in its length? E, what is its change in length? Change in its length over here, full stop, if E equal to 2 into 10 raised to 5 mm square. Now in this problem, very interestingly, the force is not applied here. Some external force is there, no? Some external force is not applied, just it is hanged, you know? Therefore first we will concentrate on stress and later we will concentrate on elongation. See, this point is there, no? This red color what I marked here, this is pulled by its weight here, you know? First we will name this bar as a 1 and this bar as a 2. Therefore a B point is there here. This B point is pulled by W2. Pulled by W2. Then W2 divided by area, if I do, then I will get a stress at a B. Okay. Then stress at a B point will be equal to W2 divided by area. Okay. Before that I will calculate A1 and A2. A1 equal to pi by 4 10 square is 78.5 and A2 is pi by 4 6 square. Pi by 4 6 square is 28.26. 28.26. Then here what is the W2? First I will write this. And what is the sigma A? Sigma A here, this red color, it is pulled by 1 and 2, both are hanging at that point. Therefore this is W1 plus W2 by A. But here area is also again A1 only, here also area A1 only. Okay, both area is A1 only. Now I need to find out W1 and W2. See, density, if this is a weight density, they said weight density will be equal to weight by volume. Weight by volume, right? If I substitute W1, then it will be V1. If I substitute W2, then it will be V2. Then it is very easy to get W1 and W2. Then W1 will be equal to V1 into gamma rho and W1 it is. That V1 is what? V1 is volume of the first bar, that is area into length. Area is 78.5 into length is 1 meter. 78.5 mm square into 1 meter means 1000 mm into that density is given 0.7644 into 10 raised to minus 3. Okay, Newton per mm cube. Therefore 78.5 into 1000 into 0.7644 into 10 raised to minus 3. This weight I got, W1 I got 60.00 Newton, only this much. Okay, this is a W1 I got. Okay, then the same way W2 I can get equal to gamma into V2. Then gamma is how much? It is 0.7644 into 10 raised to minus 3. Volume here is 28.26 into 1000. 28.26 into 1000. Right? Now this weight will be 0.7644 into 10 raised to minus 3 into 28.26 into 1000. This is 21.60 Newton. This is W2. Then sigma 1 will be equal to W1 by sigma B. Sigma B equal to 60 by A1. Sigma B equal to 60 by A1. A1 is 78.5. That is 60 divided by A1, 78.5. This is very small stress, 0.764 MPa, and sigma A, that is W1 plus W2. Therefore 60 plus 21.6 divided by A, 78.5, is 1.04. That is 1.04 MPa. You got this. Okay. Now, very important here is what is the change in its length. Change in its length means, first I will calculate it for 2, the second diagram. The second diagram is like this. It is hanging at a point B. It is hanging at a point B. Or, right? The upper bar will not contribute anything to the downward elongation, this downward bar's elongation. Therefore, ignore the top one, only B point is there here, this B point I draw here, and this is the second body. Now, second body weight is W2. No? Therefore, second body elongation will be WL by 2AE. Then this is the W2. Then W2 value is how much? 21.6. 21.6 into length. W2 length is 1000. Then divided by 2 into area 28.26 into E is how much? E is 200 into 10 raised to 3. E is 200 into 10 raised to 3. 10 raised to 3, 10 raised to 3 cancel. Now the answer is 21.6 into 1000. Sorry, 1000 is gone. 21.6 divided by 2 into 28.26 into 200. The answer is very small. That is 1.910 into 10 raised to minus 3 mm. This is delta L2. I got this expansion. But when you come to the first bar, be careful. Be careful. This is the first diagram I draw. It has its own self weight. That self weight is a W1. And this bar is hanging here. And this bar is pulled by some force, that is a W2. This W2 will not act as a self weight for the first diagram, W2. Therefore, delta L2 L1 equal to, this is because of pull force W2 L by AE, and because of self weight W1 L by 2AE. Check it. Think about it. Now substitute here. What is W2? Is the 21.6 L 1000 divided by area W2. Sorry, W2 is applied for the area 1. It is 178.5. E is a 200 into 10 raised to 3 plus this is a 60 into 1000 divided by 78.5 into 200 into 10 raised to 3. Solve this one. Whatever the answer it comes, that is your answer. Answer might be 0.0033. Check it. 33 mm. Okay. Thank you very much. Very important. Take it as a homework. If it is a 10 kilonewton and here it is a 5 kilonewton. Solve it and send the answer. Thank you.